Okay, our second speaker is Kurt Tyler from Janney at Elstner. Kurt conducts condition assessments and structural evaluations and performs structural analyses, computer modeling, and repair designs for concrete, steel, and masonry structures. He has broad-based experience in performing failure investigations of concrete and steel structures. Mr. Tyler prepares construction documents involving repair designs, creates graphical details, and repair specifications. In addition, he is experienced in utilizing non-destructive testing techniques covering various equipment and materials. And the title of Kurt's talk is Sectional, Shear Strength Analysis and Strengthening Design of Garage Post, Tension, Beams, and Girders. So I will turn the control over to Kurt.
Okay. All right. Well, good afternoon, everyone. Thanks for having me present. My topic is a little bit different than the previous presentation. This is very more specific into constructability and any reuse of an existing parking garage space for something a little bit different. So anyway. So my objectives in this presentation are to share some learnings on evaluating the shear strength of continuous post-tension structures, to discuss how the assessment of as-built conditions and the evaluation of in-situ material strengths, material properties can reduce the repair scope for repair projects, and to share detailing challenges and some best practices associated with carbon fiber reinforced polymer repairs. So a little bit of background on this this garage that we'll be talking about. It's shown here on the left in Google satellite image. I've traced the kind of the outside of not the entirety of the garage, but just the portion that we evaluated. So you can kind of see there on the left, you have some planters, some small planters, some pavers, the grassed area. And here on the right side is the original construction drawings from 1974 that show the post-tension frames that go up and down on the page, and then the pan joist system that's there in between. So, as I said, the building and the garage that we're talking about, built originally in 1974. This particular garage, there's a few garages for that building, but this one's for the visitor parking. It's all underground. As I said before, it's a post-tension continuous frames, and lightweight concrete is what makes up those frames. So here on the left is the kind of the civil drawing for the rehabilitation scope. So the existing conditions, like I said, the pavers, small planters, and then the right side shows the rehabilitation. So what was intended here is that all of that material will be removed, and they build a new kind of plaza area with larger planters and a detention basin, as well as this one-story freestanding building that was going to be a restaurant. So one of the reasons that we got involved was you have these very large planters now for much larger trees. And so you can see on the snippet from the structural drawings where they have this superimposed dead load, and you've got 310 PSF for both the large planter areas and the water detention basins. So this slide shows the section from the structural drawings indicating the extent of the structural repair scope, so the CFRP scope. And all of that is shown with that kind of dark colored hatch on the plan view of the garage. And I've kind of blown up a portion of that just to kind of show kind of why we were involved. So the magnitude of strengthening that was requested by the overall EOR engineer record was, fairly routine in some areas, but very high in others. So when you're asking for 150 kips of shear strengthening through carbon fiber, that's a considerable ask, and it may or may not be possible. Basically, we were involved because one of the contractors bidding on the project sort of approached us and said, "Hey, something doesn't seem right here. Can you guys maybe take a look at this? Maybe talk to the owner, talk to the engineer of record, just to see what's going on." So we did, and that the engineer the contractor approached us. He was on the right path. His sort of feasibility concerns were valid, and there's two kind of main concerns there. There's, is it reasonable to be able to do this with this material, with this approach, and is it allowed? So ACI 440 permits the use of externally bonded FRPs for strengthening up to a point. So your existing structure has to be strong enough to take 1.1 times the dead load plus 0.75 of the design live load. There are several of the locations that did not meet that criteria, which again it's not like you can't do the repairs. You just have to do something else, or you have to maybe use a different technique and not just throw some carbon fiber up the sides of the structure. So I believe, in the locations that needed 150 kips, I think our initial calculation showed you would need something like 6 plies of carbon fiber wrap, which is quite a lot. Typically, our sort of rule of thumb when we're going through and designing these repairs, say from the ground up, would be we would limit to no more than 3 plies. Just to kind of give some context there. Okay, so this is a snippet from the structural drawings. Now this was, we'll say, a schematic shot. And I think, the intent was always that the EOR would provide the loads and that a delegated design would occur. But if you're a contractor looking at this and you are going to be strengthening and you're getting your bid together, you're going to look at that detail and say, okay, I just need to go to the bottom of the pan joist. Well, that's somewhat problematic because, this continuous frame that we're talking about where we have these issues with shear strength, you're going to initiate flexural and flexural shear cracking, over top of your supports. And so that's going to be coming from the top. And so you're going to have a portion of that girder that is going to initiate cracking, and it's not going to be protected. So, we want to have our CFRP anywhere where we're going to have shear cracking, right? So we want to take that all the way up to the underside of the deck. So one of the other kind of issues or concerns, sort of things that we saw, was that the EOR assumed that in his what he was asking for the strengthening, he assumed that no stirrups were present because the record drawings were a little bit unclear about exactly what the stirrups were. So you can see here that this has got number 3 stirrups, but it's in an S2 configuration. So you don't really know what that is because there's no point back to what S2 was for. So, we kind of just had this sort of informal meeting with the owner and the OR and said, hey, here's what we would recommend you do. We'll do kind of a more thorough investigation. We'll see what the reinforcing steel is. So we'll do some exploratory openings. We'll do a lot of GPR to verify that basically that stirrup layout is what it says it is. We'll get actual concrete strengths and density to better understand the actual in situ properties of the concrete frames. And that's for several different reasons, which I'll get into a little bit. So, as I mentioned, our assessment involved GPR scans of all of those beams that were scheduled to be strengthened. So getting the layout, the actual layout of those stirrups. We did some exploratory openings to verify that, okay, this schedule says it was supposed to be a number 4 stirrup. Yes, in fact, it is a number 4 stirrup. And we wanted to see, okay, does it have cross stirrups? So are there legs of the stirrup that go inside the girder? And so what we found from our assessment is that no, they're actually just 2 vertical legs. So just going around the perimeter of that section. And we took core samples. I believe we took a total of 6 cores. We took them fairly long. So you can see this core is 14 inches long. So we were able to, cut that up and use part of it for strength testing and then part of it for density testing. And the reason that density testing is important, if you don't have good information on your project drawings about, okay, maybe that it's lightweight concrete, but you don't know if it's sand lightweight or lightweight aggregate. So your lambda is going to be affected. So you want to use the most appropriate and non-conservative lambda so that you're not discounting the strength unnecessarily. So, okay, we did all this work. What did it get us? What did we actually see from the assessment scope? Well, we had an assumed compressive strength based on the original drawings of 5,000 psi. You can see the compressive strength of all of those cores. And when you do the calculation for the equivalent compressive strength based on the 562, you get something closer to 6,100 rather than 5,000. In addition to that, as I mentioned before, choosing the appropriate lambda, well, the EOR had actually already assumed that the lambda was 0.85. And so basically we just validated that assumption rather than, you get an extra 0.005 and your lambda is not going to give you much additional strength, but it's certainly a good way of determining that rather than just guessing, conservatively guessing. So one of the other kind of big gains is that you get to increase your strength reduction factor, from 0.75 to 0.8 when you go through and you verify your geometry and layout of reinforcing, and et cetera, et cetera. All of that stuff gets you a better understanding of the structure, allows you to make a less conservative strength calculation, and you get to use more of the structure strength. So, and we did, now that we know the actual layout of the stirrups, the shear steel, we accounted for that strength in our reevaluation of the structure. So kind of understandably, the EOR had developed a structural model of the garage and didn't want to share that with us. I understand it's from one engineer to another. You don't want to just hand over a big structural model that you've developed and put a lot of time and money into. So what he did provide was basically the sections and the shear forces and moments at each of those sections from the structural model, and gave us basically a Excel spreadsheet of all of that information. And so what we did was we took all of that information and we developed our own calculations for each of these sections along the length of the member to determine, okay, yes, we need strengthening here, or no, we don't, based on the updated information that we have. So I've provided a little snippet of one of our pages for one of the members that we looked at, but effectively we determined the appropriate shear strength in accordance with 318, and considering, when you have a post-tension frame and you have a variable mild steel with respect to length, you have to consider whether at each of those sections, your section is adequately pre-stressed. And so all of that information has to be kept track And we find one of the best ways to do that is just with a spreadsheet like this. So another thing you need to consider is the pre-stressing position and angle with respect to the length, so that you're adequately accounting for a V sub P and also in V sub CI. So one of the obvious benefits of post-tension frames or pre-stressed concrete is that you have if it's adequately pre-stressed, you have a greatly reduced AV min. And so for these particular frames, I believe the difference between this calculated AV min and the other ones from that table are roughly a factor of 10. So you need like roughly a tenth of what you would need if you didn't have that adequate pre-stressing. And this changed throughout the length because of the addition or subtraction of the mild steel. And so all of this just has to be adequately tracked and checked. So what does that all mean? What did we get out of all of that after doing all of that actual, math? Well, we reduced the repair scope to what you can see here on the left. So anything that is highlighted is what had to be strengthened after we did that work. So, we went down by 81%. We also, because we were able to increase the strength of, demonstrate the increased strength of these members, we eliminated the need to use a non-CFRP repair approach, which is big. If you're an owner and you're looking at bids from contractors and you've only got one repair method versus two or three different types of repair methods, maybe, that's going to be a huge reduction in cost. And obviously the big reduction of cost in just reducing this repair scope. Now I mentioned before that, a lot of these areas were, maybe I did mention before, the AV min that was required was not always present. So one of the good things about doing all that GPR work is we could see where the stirrups were misplaced and where they need to be, where we need shear strengthening just due to achieving AV min. So a lot of the repairs were for strengthening, but a lot of them in some of the other locations were just to achieve AV min. So, one of the challenges with the structure, the geometry of the structure, is the pan joist system. So the way that the pan joist sits on the form on the girder, you get this little bump out, and that discontinuity is a problem if you want to strengthen the entire side of that girder. And so you basically have sort of two options. You could either grind off that entire shoulder, or you could come in and fill in that discontinuity, because one of the sort of, let's say, cardinal rules when you're doing a CFRP is you don't want to wrap an inside corner. It's just a really good way to get a debonding failure. So, we decided, okay, we could either tell the contractor to grind off every single location through our details, or we could fill it in. And both of those options are somewhat problematic. I mean, it's a lot of grinding, one, and then it's a lot of filling in. So we chose to do sort of a combined approach where we partially shave off that shoulder and then fill in whatever shoulder remains with just a small cant of material and a cementitious repair mortar. But if you're dealing with a lot of surface applied mortars, you're losing, or you're trusting making that repair mortar bond critical. And so we just wanted to minimize that through this detail. So this is sort of what that looked like prior to being canted on the left, and then that small repair material cant on the right here. So as I mentioned before, you know, whenever you do have this change in geometry, you have an opportunity for a debonding failure. So one of the things that we always detail, if we're going to have something, any kind of discontinuity, we want to have, you know, a splay anchor. So the splay anchor just prevents that kind of the debonding of failure at that discontinuity. It also allows you to use an increased factor when you're calculating the strength of that repair. So it's dually important. And with any concrete repair, quality control is vital to success. So, you know, for CFRP repairs, you want to have a certain surface profile of your prep surface, but you don't want to damage it from the preparation. So, you know, we did substrate preparation testing, just evaluating, make sure that we're going to have adequate bond of this parent concrete. With all things, you know, mock-ups are your friends. So here's just a few photos from the first mock-up. And so, you know, this is a bond critical repair. And so you want to make sure that your CFRP has adequate bond. So always test. And here are a few shots of the finalized repairs. You know, unfortunately, I wish I could show you a photo from the top side of the plaza with that new restaurant and those beautiful big trees. But unfortunately, the project was postponed after they finished the repairs to the garage structure. The strengthening is basically right when COVID started. So.
Hey, thank you, Kurt.
Thank you.